Yeah, thank you very much. I'm really happy to be here. These Bitkom events are, for me personally, always good experiences where the whole actually community, scientific community, but also transfer community, startups, and established companies can meet to discuss the relevant topics around AI and quantum computing. And I'm going now, and this very nicely fits to the previous talk, I'm going to discuss an idea and show you some research results also from the German Research Center for AI and how we actually brought these two topics together, quantum computing and AI, in the specific context of human-robot collaboration. And this might sound a little bit bizarre. We believe actually that aspects of quantum computing can help actually also to reshape the way how we will interact with computers, how computers can take into account also relevant aspects of us as human beings. Of course, if you see towards in the title, you know there is nothing to be bought yet. That is not even R&D development stage. This is early research in a way, and the German Research Center for AI actually has this kind of specific mission to gap this bridge between basic research and applications. We work in our projects with many actually industrial partners, smaller ones, small SMEs, large partners, and so on. We've been founded at the end of the 80s with the same title, German Research Center for AI. Of course, the AI has changed completely. You know, quantum computing at that time was just basically a sketch idea, and we've come a long way. And together with actually our partners and shareholders of DFKI, we try to continue this path. You know, Thomas Jatzombeck also mentioned that that we have very strong research here in Germany. This is true. We are part actually of the Excellence Center network that we have. You know, the 6 different kind of AI excellent centers, competence centers, and but for us, it's also important to keep a little bit in mind, you know, what society, what industry needs, you know, and how we can make use of these kind of very early research results, how we can transform them into societal impact. And this, I guess, is still the homework that we have to do here in Germany. That's why I also referred to this 18 months time window. I think the general landscape has improved, but there's still lots of room for improvement, of course. But anyway, DFKI, as a public-private partnership, tries to contribute in this respect. Those are our shareholders. I'm not going to, so some of you are here also, I know this, and I'm going to talk today about this kind of intersection of AI and quantum computing. And in a way, this combination is also a very adds interestingly to this new era of AI. On the one hand, we have this kind of term of quantum AI. And the interesting part is, why would somebody from AI look at quantum computers? The main reason is that many problems in AI are very difficult and hard problems. And quantum computing gives this promise that maybe some of those hard problems can be solved in an optimized way, rather than just having kind of good solutions, you know, so we get optimal solutions eventually. And this is in particular then necessary when we have many, many parameters, many, many variables to look out at simulations, for example, that we have, in particular, when we are trying to build digital twins of the world. You know, the higher the fidelity of the digital twin, the more parameters I have, the more complex are the simulations, and if there's a high amount actually of time variability inside, so things are changing quickly, then all kind of classical simulation approaches basically fail. We just have then rough actually approximates. Of course, machine learning, data-driven approaches can somehow help a little bit. And it's, of course, an interesting question to which level machine learning can basically compete also with helping to solve complex problems that quantum computers are going to solve. So we call this Twin AI. Twin AI is actually this kind of closing of the loop of these kind of more, at the moment, very monolithic kind of AI systems that learn, and then they are basically more or less, and they learn, of course, from data, but they don't learn by experience, by their own experiences. They learn actually from experiences from others, some data that has been collected. That's usually static, And if you break this up, the systems get more intelligent. They get, in a sense, that they are more adaptable to changing environments, and eventually to a point that they nicely fit also into our human society with its many different parameters, influences, that they fit to the specific needs of users, and of course that they fit to many kind of applications, from medicine, industrial production systems, and we've heard some very nice examples also that IBM is working on in material science, for example. Yeah, the quantum revolution in machine learning as being also one of the hard problems is, of course, in itself interesting, to look at from a quantum computing perspective, but in particular relevant, and I would like to talk about this, is this kind of synergy. So on the one hand, we have what I call quantum user modeling. So of course, user modeling is everywhere, more or less, but on a very coarse level. So we're not talking, there is currently no approach that can model a single human being in all aspects, physiological aspect. So this is not possible, from a full medical digital twin, but of course, not in a mental aspect, to have a full, actually, digital twin, actually, of your mental states, for example. But, of course, we are kind of trying to do this. We're trying to reach into that direction, and quantum computing might help here. Then also the interaction between systems and humans might change. I have one example here about safe navigation. It's still very hard to build robots that are navigating safely in the vicinity of humans. There are different ways to do this. Either you build a robot that is very fluffy, so it can do not much, so it also cannot do harm, or you build it very powerful, then of course there is this very high risk, so that it kind of hurts somebody if something goes wrong, so it's not operating safely, and but then again, they are usually very slow nowadays. So again, this is also something where quantum computing might help. And then also in the interaction in real time, when it comes to very fast actually interaction cycles, you can use control theory. For example, at Hannover Fair, we've shown a robot that you can throw things at, and the robot can throw things at you in a very limited scope. We humans are much more flexible, in terms of what we can do, from very coarse, actually, operations, lifting heavy stuff, to very fine-grained operation. And maybe here also quantum computing might help. I will give you a couple of examples that come from the different labs at DFKI. This is now an example that comes from our lab in Bremen that concentrates on building next generation robots. And this is about using deep reinforcement learning with quantum technology for safe robotic navigation. So safe robotic navigation means that it can move safely through a space. It can basically take into account what humans are doing in that space, and it basically is safe for the humans. And it finds the optimal solution to be safe in this respect. And if it knows it cannot do the operation safely, it won't do it. So that's the idea here. And so you have a very complex setup And again, this is research, this is basic research at the moment. You have complex setup where you have sensors that constantly monitor actually the environment. And of course, you use techniques that we know, deep reinforcement learning, but on the same time, we look actually at the role of quantum that quantum computing can play here, and how we can improve actually classical approaches by using quantum computing. And this basically leads to, and this is actually work together with a department in Saarbrücken. This leads actually to these kind of safe paths that robots then can navigate. And of course, there are classical methods that one can use, but it's pretty interesting in general to look actually at compare the quantum solution to the classical solution. This here is called NavQ, which is, and I will talk about this in a second again, is actually a hybrid quantum classical system that uses both kind of classical approaches and quantum approaches. Again, this is also something that makes a lot of sense in a way that we also use deep neural networks in combination with classical, I would say, modeling of the physical world, so not data-driven, but knowledge-driven in a sense. So if you think about classical differential equations that you use to model certain physical properties, and you combine this actually with data-driven approaches through a deep neural network. And this leads to competing results, which is pretty interesting. So you can build systems that use quantum computers to safely navigate, in this case, a robot through the environment. And in some aspects, it's absolutely comparable. In some aspects, it does work a little bit less efficient, actually, but in general, it's very promising. So this is something to further explore, Since we know that the amounts of states that we can explore in parallel to a quantum computer is much larger than anything else that we can do. And of course, you can use quantum computers also to simulate a very complex situations. For example, here, fluid dynamics. Again, for twin AI, for example, in the medical sector, it's very, very useful. Here's an example of a flow within an aneurysm that you want to try to simulate as precise as possible to make really the correct medical diagnosis. And this could be built in then into a digital twin of ourselves, for medical purposes. So this is not so much about the interaction, but this is more about ourselves. And of course, it could be used to a certain extent also to interact with the environment. Maybe not the aneurysm, but other aspects here. So this is a very relevant area where quantum computing is promising and very helpful in terms of building a digital twin of ourselves and the interaction with the environment. So, what are here technical challenges? So in general, building a digital twin, we know this, industry has gone pretty far away now to digitize actually production processes, for example, and so on. We know this. But as I mentioned, those often are static, and we need to build systems that are much more dynamic, that learn by themselves, that update the digital twin, the twinned representation through interaction with the environment. And this then leads to the handling of complex tasks, to a better understanding of the situation, and in the end, what I would consider the goal actually of building intelligent systems, it leads to an adaptation to new situations in general. I think this is very important. And this is often something that even nowadays large foundation models, when you present them with completely new situations, they often struggle. Not always, but if they are presented with something that is completely out of the box, they often struggle. And systems that are used to learn through interaction with the environment are much more reliable in this respect. So, how can we combine these two paradigms? So, one thing is they're generally completely different computing paradigms, and also we have different timescales here. What we can do is we can try to build so-called hybrid architectures that consist partially of more what we know, classical AI systems, data-driven learning systems, as I mentioned. It's a little bit a trick how you handle the resources, and I will give you two course examples how you could do this, how you could basically combine these different scales. And this is actually through more or less ideas that we borrow from also classical computing, for example, from distributed computing. So this could be something to leverage actually on top in the future, of course, on top to have kind of distributed quantum computing that is combined then with classical distributed computing. Yeah? So this would then lead to novel reallocation algorithms, methods to leverage this kind of parallelism. So quantum computing, in a sense, since they're running physical experiments to a certain, then are already pretty parallel in a way, but you could push this one level higher. Yeah? And of course, this could also lead to better error correction and so on and so forth. Yeah? So this kind of distributed quantum computing is one way. Another idea that also comes from classical algorithm theory is quantum coalition formation. So you basically decide on the fly which kind of entities work best together. This could be, for example, used, this is something that is used also when you have kind of swarms of satellites and you need to reduce actually communication costs. You start to think about which satellite should first communicate between each other before then this kind of different coalition communicate with the base unit. So this is something that we are also working on. It's something also that is the ASR group in Saarbrücken. We are already kind of, in a way, since we don't have a quantum computer, as I said, we are relying, of course, on the great work from IBM and others, in that area. But the nice thing is we can work with simulations. That's, this kind of abstraction layer is very helpful for us to at least, not in the end build the systems because they are far too slow, but to understand the concept. This is very important. But of course, we're also building prototypes. Here's one that is based on the distributed computing concept here. And it's something where we combine different abilities, for example, the pre-analysis abilities of a single mobile sensor, in this case mounted on a drone, that tries to classify different types of raw materials that are used for steel processing. This is a project with Saarstahl here. And the idea is that by combining actually the clever pre-processing on the drone itself and the power of the supercomputer and eventually a quantum computer in the background, you can save lots of energy and also processing power in this respect. Okay, in the last 2 minutes, I would like to talk a little bit about what kind of ethical considerations one would basically think about, when you combine actually these kind of quantum approaches and AI approaches, in particular when it comes to human-computer interaction, human-AI interaction. So one, of course, is data protection and privacy. While I believe that sometimes, especially in Germany, we're just overdoing it a little bit too much, by just always considering data privacy first, it is clear that once a very high fidelity simulation of yourself is possible or close to possible, this kind of data has lots of value and is also pretty critical, so it's something to think about, of course, Then transparency and explainability, are those better, for example, these systems as classical, purely data-driven systems? And then the question is, how would actually society change? What kind of jobs and so on will be necessary? And for all these kind of different aspects, there are solutions. So there is actually also for quantum AI a path towards explanations and explainable AI. In a sense, since we are talking about states here, it's maybe even a little bit easier in a sense, as with a classical large neural network that often operates more like a black box. So it's something that is interesting and we're working on. And then, of course, to bring these things together, there are different steps to do. So we're at the beginning actually of a roadmap. So proof of concepts and implementations are currently underway. But I believe in the next year we will see first, very similar to what we've seen in the earlier talk, we will see first niche applications working, alongside improved quantum hardware and also the algorithms. And so I believe maybe in 3 to 5 years we will see these kind of first twinned AI quantum frameworks, that kind of allow us to improve these kind of interaction between intelligent system and human systems. And then, of course, on the long term, this could change the way how we do medicine. This could change the way how our infrastructure works. So we have a kind of eventually fully integrated human-machine teams, because the machines understand the humans very well, be able to simulate, operate safely in their vicinity, and so on. So there will be large impact, of course. So it's a high-risk, high-gain research in a certain way on various industry. Healthcare I talked about, but also production industry 4.0. Very adaptive and flexible production lines. And in the end, of course, this will also have an impact on education and the way how we have to basically, on the one hand, we can use these techniques to build much better, very personalized and targeted education systems. On the other hand, of course, we need to basically train, the next generation of AI experts in this area also of quantum AI, which is currently still not happening in a broad scale. And with that, I hope this was entertaining, and I thank you for your attention. Thank you very much.